All right, guys, in this video, we're going to be looking at the van der Waal forces, okay? These are forces of intermolecular attraction, and they explain some of the behavior that we see in bonding, but they're also really important that we understand how they impact molecules as they interact with other molecules around them, all right? So let's look at the van der Waal forces. So the first van der Waal force is called dipole-dipole attraction. Now, obviously, you've seen the word dipole before. We know what polarity is. And when you have two dipole moments near each other, they will interact. Just like if you had two magnets near each other, we would expect them to interact. So a dipole-dipole interaction happens between two polar molecules. And a great example of this, okay, is right here between this S atom, this sulfur atom, and this hydrogen atom right here. So this dotted line is showing an interaction. All right. Anytime we see a dotted line between two chemical species, we're showing an interaction. Now, it looks like it might be a bond, but it's not a bond. Okay, it's just a force of attraction. That's the difference between a dotted line and, that straight bar line right there. That's a bond. Okay. This is just an interaction. Because it's between two molecules, we call them intermolecular. Wow, molecular. There we go, my pen's all over the place right now. Anyway, a lot of times when you get many molecules together, they can all start to interact. So you can kind of see this over here. That's why it's really interesting to try to predict what molecules are going to do, because we see the macro scale, right? We see billions and billions and billions of atoms, and we can't always see with our eyes the interplay that's occurring beyond our ability to resolve, right? The spaces that are too small for us to see between. So something that we should keep in mind, like let's say you're looking at distilled water. It's sitting there. It looks like it's completely still. Well, inside that distilled water, the water molecules are interacting. Okay, they are undergoing attraction, like between this negative end and this positive end. They're also going repulsion, like between this two negative ends right there. And the next kind of interaction we're going to look at is called dipole-induced dipole. All right, and in this you have one polar molecule and then a non-polar molecule. And the word induce means to cause, right? Or to force something to happen, right? If you induce someone to go into labor, that means, you make them start to deliver their baby. If you induce a reaction, then you have two things sitting in a reaction vessel and you maybe add heat or stir in order to get them to react. If you induce a dipole, then you cause a dipole to appear that didn't appear before. So here's a great example of it. We have a water molecule on the right, and we have an oxygen molecule on the left. Now, normally, O2, right, if we draw the Lewis diagram for O2, it's completely nonpolar, okay? The electrons are evenly balanced, right? If we draw a line through the middle, there's no unbalanced electrons. If we draw a line this way, no unbalanced electrons, right? We could even draw a line through, there's no unbalanced electrons. But when you put water near that oxygen molecule, the lone pairs, right? So here are our lone pair electrons. Those lone pair electrons repel the electrons that are normally around this oxygen molecule, or atom rather, right there. So the electrons start to move. Well, when they do that, they all accumulate over here, and I end up with a partial negative charge, and I have a partial positive charge on the right. I have induced a dipole. Well, once the dipole has been induced, and this side is positive, and this side of water is a partial negative, well, there is my dipole-induced dipole force of attraction. Okay, so that's a dipole-induced dipole. We see another one right here between argon, which is a noble gas, totally inert, shouldn't interact with anything. But if you put hydrochloric acid near it, the chlorine atom, all right, right here, it has this negative side. It's going to force electrons on argon away, and it's going to actually attract towards the nucleus of argon, which is positive. So that's a dipole-induced dipole interaction, a van der Waal force. London dispersion forces are the third kind. They are temporary dipoles that appear in non-polar molecules. They happen all the time to all molecules, and they're totally random. So we know that electrons move. It would be nice if they were always like equally distributed around the nucleus, right? That would be nice, but they don't. Sometimes, just for a brief moment, all the electrons have appeared on the right side of this molecule. And so we definitely have a dipole that has appeared by random chance. Well, the moment that I get a random event in molecule number one, right? So we'll call this molecule one. It's the same molecule right there, right? These are the same molecules. Then the molecules around it experience this negative charge. So this is molecule 2, and this negative charge forces the electrons away. It results in a delta positive, right, on the left, and so I get a force of attraction. This happens in all molecules. It's one of the reasons that molecules move all the time. Okay, they're constantly experiencing London dispersion forces. Hydrogen bonding is a special kind of dipole-dipole interaction. Now, it's called a hydrogen bond. This is actually a falsehood. It's not a bond. It's just a van der Waal interaction. Okay, it's a force of attraction. It's not a true bonding. There is no exchange or sharing of electrons that takes place. It only happens between molecule 1, which has to have hydrogen on it, and F, O, or N that's hooked to molecule 2. Okay, so water is a great example of hydrogen bonding that can occur. I have oxygen on molecule 1. I have, well, actually, I guess we'll say oxygen on molecule 2 there, and we have the hydrogen on molecule 1, right? And it doesn't matter that it's the same chemical, it's just two different molecules have to be interacting. And because oxygen has this partial negative and hydrogen has this partial positive, there is my hydrogen bond. It's a force of attraction. That's pretty strong, okay? In fact, it's so strong that it actually sets water up to freeze in a certain pattern. So there are hydrogen bonds symbolized in this model I'm showing you on the screen in purple. So I'm going to make my face a little bigger here. So these purple bonds, right, these purple sticks, these are hydrogen bonds. And as water cools down when it freezes, the hydrogen bonds orient the molecules into a certain pattern. And so if I step back and hold this up, you can see that they stack in these kind of honeycomb arrangements. And it's this empty space in the middle where air can get trapped that actually leads ice to be less dense than water. So hydrogen bonding, it definitely, exists. It definitely, impacts our molecules, but it also can lead to things that we see in the real world around us at the macroscopic scale, right? Macro meaning big. Now, the other thing that these van der Waal forces, affect in the macroscopic world and the world that we see around us are boiling points. So hydrogen compounds that are able to hydrogen bond have really high boiling points. And that's because those forces of attraction hold the molecules together, right? So if I want to go from like a liquid to a gas, then I need my molecules to spread way out, right? I need my gas molecules, they're moving apart. Well, hydrogen bonding is a force of attraction. It holds them together. So not only do you have to give enough energy, right, to get the water molecule to vaporize, you also have to give it a little extra energy to overcome those like attractive forces that are holding the water together. So H2O, HF, and NH3 can all hydrogen bond, and we see that compared to the very next compound that the hydrogen can bond to, their boiling points are significantly higher. And in fact, were it not for hydrogen bonding, we would expect H2O, right, if we're following this trend, we would expect H2O to have a boiling point like near like negative 100 Celsius, which would mean there would be no liquid water on Earth. There's only liquid water on Earth because of hydrogen bonding, right? This trend right here, maybe not quite that low, but that trend line right there goes down, 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 down. We would expect it to vaporize somewhere down here in the negatives, which would obviously prevent life as we know it. Some other things that van der Waals impact, besides the boiling point, are surface tension, right? More hydrogen bonding equals better surface tension because, again, everything's attracted. Evaporation, again, just like boiling, I have to overcome those forces of attraction in order to go from a liquid to a gas. Vapor pressure and viscosity, right, are also impacted by van der Waals forces because, again, they're holding molecules together. So here's some practice. Here's what I want you to do. I'm going to give you some molecules. You should write down how those molecules are interacting, like what van der Waals force would be in play. So we'll do the first one together. I have some H2, a sample of, so we'll say a sample, there we go, a sample of H2. It interacts by London dispersion. All right, how do I know that? Well, I've got H2, and I have another molecule of H2, right? I've got to have at least two molecules in my sample in order for them to interact. It's not polar. There's no dipole moment. So the only way that these two things can interact is if all of a sudden I get a random, so I'm going to put a little R right there, a random dipole, and another random dipole. That's the only way that would work. All right, Ne and Ne, two neon atoms. Well, are they polar? No, right? Must be London dispersion again. C2H4Cl2. All right, this is a complicated looking molecule. C2, all right, probably looks something like this. All right, does it look polar? Can we draw it out and look at it? Yeah, all right, dipole, dipole, okay? The Cl, the chlorine, is definitely going to take away from our molecule. It could also, let's see, it could also look like this. Who knows, right? HF. Well, hydrogen fluorine. I know that fluorine is one of the fun molecules, right? H to F, probably hydrogen bonding. All right. NF3. Well, there's no H, so it can't be hydrogen bonding. When we draw it out, and we would need to draw it out, we'll find that it's dipole, dipole. So nitrogen gives us 5. Fluorine gives us 7, and we have 3 of them. So that's 21. So I have a total of 26 electrons. So that's going to look like this. Each fluorine is going to end up with 8. 8 and 8 and 8 is 24, plus 2 makes 26. So I definitely have an unbalanced level of electrons. So that's a polar molecule, dipole, dipole. C6H6. Well, that's going to be London. All right, C6H6 actually looks like this. It's benzene. Each of these carbons has a single hydrogen bonded to it. And like most organic compounds, it's not polar. So, or like many organic compounds, it's non-polar, so it's London. All right, now number 7 is one that we should look for often because it only has one answer possible. It's got 2 different molecules. It's got HCl, which hopefully by now we recognize HCl as a polar molecule. And it also has C6H6, which we just looked at, right? This hexagon-looking thing here. Normally in organic we don't draw the hydrogens, but because we haven't done organic yet, I'll go ahead and draw that. So I have a polar molecule, and I have a non-polar molecule. And there's only one force that acts between polar and non-polar, and that's dipole-induced dipole. Number 7, like the dipole-induced dipole answer, it's never the answer if you only have one kind of element or one kind of compound in your sample. So 1 through 6, you'll notice it's only one kind of compound. So it can't be dipole-induced dipole. A molecule can't be both polar and non-polar. So the only time we should ever put dipole-induced dipole as an answer is if we have 2 different chemicals interacting with each other. doesn't mean that's the only answer you can have, right? Let's say I had HCl and I had H2O. Well, actually, between these two, I could get some hydrogen bonding, okay? So it could still be hydrogen bonding, it could still be something else, but it's only going to be dipole-induced dipole if you have two different elements, or two different compounds. That's the only time that's an option. All right, so if you have any questions about those, feel free to send me an email. I'll be glad to help you guys out.